So now that we've talked about countdown latch and we've talked about cyclic barrier, it's time to turn our attention to the third and final form of Java barrier synchronizer. Now, of course, there's other barrier synchronizers in Java, like you can spawn threads and then wait for them to finish with thread join. That's a simple version of a barrier synchronizer. But when we think about classes that are intentionally designed as barrier synchronizers, it's countdown latch, cyclic barrier, and phaser. So that's what we're going to talk about here. And I sometimes wonder whether they came up with the name phaser because they were Star Trek fans or something like that. But you'll see why it has the word phaser. Phaser is yet another Java barrier synchronizer implementation. And what makes it a little special and a little more complicated is it allows for a variable number or a fixed number of threads to wait for all operations performed in other threads to complete before proceeding. And an example I like to use here, it's a little harder to find a good human known use example, but I think this one's probably okay. If you had people building a house, you might have different work crews. You might have the foundation crew who pours the foundation. You might have the framing crew that puts the wood on. You might have the roofing crew. You might have the electrical crew or the flooring crew or whatever. And those crews might not have the same number of people. One might have 5, one might have 2, one might have 11, who knows? And the crews show up and they work in phases, and you may have a variable number of workers per phase, but it still may be the case that you need to wait for everybody to show up to start working because you need them all there for some reason. So the way to think about this is you've got phases, you've got work crews, but you may have different number of workers per phase or per crew. So that's kind of a way to think about it in a human known use style way. Phasers are well suited for variable sized cyclic entry and or exit barriers, where the number of parties can vary dynamically between work crews, if you will. You can use phasers for fixed size parties as well. However, it's probably overkill. Maybe a little hard to see this, but this is it's a minivan full of seatbelts, and it says overkill. Why have one when you could have 200? So it could be more than you really need to have a phaser for a fixed size number of parties. If you have a fixed size number of parties, you're probably best off just sticking around with cyclic barrier. But for the cases where you need more complexity, more sophistication, phaser could be your cup of tea. A phaser does not implement any interface, just like a cyclic barrier does not. It does not apply the bridge pattern. It does not apply the abstract queued synchronizer framework. Instead, it defines some fields, and in particular one field that is used to provide the semantics that a phaser needs. And it's a very interesting field. The phaser has a volatile long. Anytime you see something called volatile long, the first thing that should come to your mind is, I bet they're going to be packing bits into this and doing atomic operations on it. And that's exactly what's going on there. It's basically using this volatile long as a bit field, or a set of bit fields. And there are 4 of them. One of them is the unarrived bit field, which keeps track of the number of parties yet to hit the barrier. So that's 0 to 15 bits are used for that. So that gives you a sense of it's bounding the number of things you can actually wait for. I think you can't have more than, 32,000 of these things or whatever, of parties, which would be quite a lot. Yes, that's 32,000 threads. Then there's the number of parties to wait for before advancing to the next phase. That's kind of like the count, the party count. There's the phase itself, which is the generation of the barrier. And you can see that this is from bits 32 to 62. So that's the number of iterations you can have, number of phases you can have in this particular phaser. And then the final bit is the terminated bit, which is set if the barrier is terminated. So it needs to either be true or false. That's bit 63, which is also known as the sign bit. And the way this works is all these values are packed into a single long that's volatile, which means that reads and writes to it in total are atomic, and it's updated using compare and swap operations. So we've talked about compare and swap before, and that's where you can atomically update something. So that's how we can make sure that the values are managed atomically, by using compare and swap. And remember, in Java, this is a bit obscure, but in Java, a long is guaranteed to be 64 bits, but 64 bits may straddle a 32-bit bus boundary. Not that there are many 32-bit microprocessors left anymore, but if you have them, the Java virtual machine has you covered. And if you define something as volatile, then it ensures that under the hood, there are operations that work on this atomically.